After studying this module, you shall be able to understand the meaning of factor rotation, know how factor rotation is done, know what oblique rotation is, understand the scree test and how to calculate scree point, understand the interpretation of the extracted factors. The purpose of factor analysis is to identify salient features that account for the majority of the variance of a group of scores on different tests. Once factors have been extracted, it becomes essential to decide how many factors to retain for rotation. Over extraction and under extraction of factors retained for rotation can have harmful effects on the results. The goal of rotation is to simplify and clarify the data structure. Rotation may be orthogonal or oblique. Orthogonal rotations produce factors that are uncorrelated. Oblique methods allow the factors to correlate. In the following module, orthogonal and oblique rotations have been discussed. This module also focuses on the interpretation of the factors by analyzing the loadings of each factor on the variables. Rotation of the reference axis. For the purpose of simplifying the interpretation of the obtained factors and also to increase the number of high and low positive loadings in the column of factor analysis, a procedure known as factor rotation is used. There are two basic methods, orthogonal rotation and oblique rotation. Orthogonal rotation method is employed when the factors are not correlated with one another, while the oblique rotation method is employed when the obtained factors are related to one another. Factor analysis, like Guilford, prefers orthogonal rotation, while Thurston or Cattell prefers oblique rotation. To derive the loadings of the factors in the case of rotated matrix, graphical method is used. Rotated factors x and y can be converted into standard measurements by spacing deciles along the new axis from 0.00 to 1.00 in the same way as was done in the case of original factors. Now, a perpendicular is drawn from the point on each rotated axis x and y to the point corresponding to the test or variable. The point where this perpendicular touches the new rotated factor axis is the loading value of the test on the rotated factor. The other method to compute the factor loadings of rotated factor matrix is mathematical. The rotation of factor x can be understood with the following linear equation, that is Rixi is equal to A1 Rix plus B1 Riy, where Rixi are the rotated loadings on x, Rix is unrotated loadings on x, Riy are the unrotating loadings on y, and A1 and B1 are weights for the rotation. The weights are the cosine of the angles of rotations of x1 with x and y respectively. Hence, in this case, A1 is the cosine of angle x1 with x, which is cos 47 degrees is equal to 0.682. Cosine of angle x1 with y is cos 43 degrees, which is 0.731. Similarly, one can also form a factor as a linear combination of a large number of factors. Hence, a rotated factor loading x1 could be computed from a linear combination of three factors as Rix1 is equal to A1 Rix plus B1 Riy plus C1 Riz. It is difficult to find weights by graphical comparison in case of more than two factors because the rotation is simultaneous in more than two dimensions and consequently the weights cannot be obtained by the movement of factor vectors on a graph sheet. Likewise, one can find the factor loadings for the rotated factor y as follows. Riy1 is equal to A2Rix plus B2Riy, where Riy1 are the rotated loadings on y, Riy are the unrotated loadings on y, and Rix are the unrotated loadings on x. A2 is the cosine of angle y1 with x, B2 is the cosine of angle y1 with y. If the unrotated factors are orthogonal and the rotated factors are also orthogonal, then the sum of the products of weights must be equal to 0, that is A1 A2 plus B1 B2 should be equal to 0. If there are four factors and the unrotated as well as rotated factors are orthogonal, then A1 A2 plus B1 B2 plus C1 C2 plus D1 D2 is equal to 0. If the above condition is not true, that is A1 A2 plus B1 B2 is not equal to 0, then x1 and y1 are not orthogonal, that is the correlation between two factors is different than 0. Oblique rotation. In the previous section, the orthogonal rotation with the assumption that the original factors as well as rotated factors are orthogonal has been discussed. In reality, there is no necessity to maintain right angles among rotated factors. There is another rotation known as non-orthogonal or oblique rotation. It is the rotation when the angles among the factor rotate from 90 degrees. In this, the cosine of the angle between x and y is 0.342, which is the correlation between the two factors. The loading of the rotated oblique factors can be obtained in the manner as was done in the case of orthogonal factors. In case of oblique rotations, the sums of cross product of weights for rotation of two rotated factors would not be equal to 0. Mathematically, A1 A2 plus B1 B2 is not equal to 0 for oblique rotation. Further, if oblique rotated factors are rotated again, then the sum of the square weights for rotation would be 1.0 only by chance. To explain the point further, the geometric representation of the unrotated and the rotated factor matrix for factors 1 and 2 respectively are presented. The geometric representation of the first factor shows the variable 1, 2, 3 and 6 are all positive and the vectors lie within the first quadrant of the circle. Variables 4, 5 and 7 fall in the fourth quadrant of the circle, which is displayed in the figure. When the factors were rotated following orthogonal rotation, all the vectors turned out to be positive and they all fall in the first quadrant of the circle as displayed. The communalities for each variable can be obtained from the figures with the help of Pythagorean theorem, which states that the hypotenuse square is equal to the sum of the square of the perpendicular and the base of the right angle triangle. The square of the perpendicular and the base of the right angle triangle give the factor variances, which when added give the communalities. Scree test. Scree test is the method to decide about the important factors to be interpreted or retained from the extracted factors. The Scree test is conducted to determine which among the extracted factors is actually contributing to the variance and does not measure random error. This test was first proposed by Cattell from the practical observation that factor variance levels off when the factors are largely measuring random error. the number of factors is plotted against the proportion of the variance extracts. The curve fitted to the plot of these factors will have a decreasing negative slope until the random error factors or trivial factors are reached. Then the curve will level off and the incremental difference between successive factors will be about the same. Cattell called the test scree test since the random error factors in a plot like that shown in the figure resembles a scree, that is, the debris that has fallen or been eroded off by a mountain and lies at its base. The factors which are at the right hand side of the factor cutoff point, popularly known as scree point, are dropped, while the factors towards the left hand side of the scree point are retained for final usage and interpretation. Presently, the scree test is the most often used technique to decide about the important factors to be extracted for factor analysis. In a problem involving 38 variables, factor analysis was used to extract factors with the help of a computer statistical package. The cutting point of eigenvalue was kept at 1 to extract the factors. On the basis of eigenvalue of 1, 15 factors were extracted. Interpretation of these factors was found to be a difficult proposition. To reduce further and to retain only the very important factors, scree test was used. It is clear from the scree point that the first 7 factors are important for the purpose of interpretation, that is, the factors that lie above the scree point on the plot. The remaining 7 factors, that are factor 8 to 15, are to be eliminated from factor interpretation because these are not contributing much of the vector variances. Interpretation of the factors. After the statistical computations of factoring and rotation have been completed, the next problem faced by the investigator would be the interpretation of the factors. This is achieved by inspecting the pattern of high and low loadings of each factor on the subtests or variables. It is to be remembered that the higher the loading, the more important the factor on the given variable or test. Let's look at an illustration which elaborates factors. So for factor 1, there are 9 variables. These variables are 1. Upmanship lifestyle, exploitative lifestyle, domineering lifestyle, conservatism, political, social and economic gain, marriage and interpersonal relations, religiosity, individualistic lifestyle and defiant lifestyle. The various loadings for each of these variables are 0.876 for 1 upmanship lifestyle, 0.869 for exploitative lifestyle, 0.755 for domineering lifestyle, 0.656 for conservatism, 0.494 for political, social and economic gain, 0.444 for marriage and interpersonal relations, 0.439 for religiosity, minus 0.657 for individualistic lifestyle and minus 0.658 for defiant lifestyle. It is observed that the above factor is a very complex factor consisting of 9 variables in all. Among these variables are 5 lifestyles, 2 dimensions of caste prejudice and conservatism. The highest positive loading is that of the 1 upmanship coping style. This positive loading indicates an individual or operator who uses his wits to get the better of people. The second highest positive loading on the exploitative lifestyle indicates attempt to get ahead by exploiting others. The positive loading on the domineering authoritarian lifestyle reflect the attitude, I know best, and you should do what I say. Positive loading on conservatism reflect the desire to preserve old beliefs, customs and traditions and to vehemently oppose progress or change. Positive loading on political, social and economic gain PSEC and marriage and interpersonal relations MIR reflect the existence of caste prejudice, more specifically in the form of expecting political, economic and social privileges within one's caste. Positive loadings on the religiosity are indicative of the existence of religious orientation with an emphasis on the concrete and literal qualities of religious belief. The negative loadings of the individualistic and defiant resistive on the factor indicate that such individuals do not have the desire to be distinctively different and individual, and neither do they possess the to hell with you attitude. In light of above discussion, this factor may be named as the going against people factor. Let us look at another example. A factor having significant loadings on 4 variables of obedient versus assertive, expedient versus conscientious, shy versus venturesome, and group dependent versus self-sufficient. The factor loadings on each of these 4 variables are minus 0.694 for obedient versus assertive, minus 0.778 for expedient versus conscientiousness, minus 0.489 for shy versus venturesome, and minus 0.506 for group dependent versus self-sufficient. The above factor has negative loadings on all the 4 personality variables of Catel's 16PF test. They are namely Catel's factor E, that is obedient versus assertive, which indicates dependent, a follower who to take action goes along with the group, tends to lean on others in making decisions, soft-hearted, expressive and easily upset personality. Catel's factor G, expedient versus conscientious, the negative loadings on factor G indicate a weaker superego strength, one who evades rules and feels few obligations. Catel's factor H, shy versus venturesome, on which the negative loadings indicate the person to be restrained, diffident and timid, and Catel's factor Q2, group dependent versus self-sufficient, the negative loadings on which indicate a joiner and second follower. In the light of this interpretation, the above factor having significant loading on 4 variables may be named as dependency and superego. Let's look at another example in which 2 variables have significant loadings on the extracted factor as given. Perceptual self has a factor loading of 0.92, whereas the variable ideal self has a factor loading of 0.90. This factor is found to have significant positive factor loadings on the perceived self. Both these variables are components of self-concept, and hence this factor can be named as self-concept factor. The perceived self is the way one perceives or describes oneself or what one thinks about oneself, whereas the ideal self reflects to the part what one likes to be. In another study, 200 college fresh graduates were administered standard progressive matrices SPM, the need achievement inventory and Torrance test of creative thinking. The significant loadings on the first factor are 0.43 for scholastic achievement, 0.54 for the intellectual capacity variable, 0.09 for the need achievement factor variable, 0.78 for the fluency variable, 0.71 for flexibility variable, 0.68 for the originality variable, 0.71 for the elaboration variable, and 0.80 for the composite creativity variable of the factor. The significant loadings of this factor are on scholastic achievement, intellectual capacity, and creativity, along with the components of creativity like fluency, flexibility, originality, and elaboration. The main variables having the highest factor loading was creativity, which includes fluency, flexibility, originality, and elaboration. All these measure divergent thinking. The other variables to be taken into account for the first factor were intellectual capacity and scholastic achievement is loaded both on convergent and divergent thinking. Keeping this in mind, this factor may be named as creative potential. This name is given because the main variables with high factor loadings refer to the creative thinking and reasonable factor loadings on variables like intellectual capacity and scholastic achievement. The term creative potential is chosen as the common ability that runs through all the variables taken into account is the capacity for creative thinking and capacity to action. A factor solution with as many factors as variables would score highly on the amount of variance accounted for and the accurate reproduction of correlations, but would fail on economy of description and explanatory power. The centroid condensation method of factor extraction involves calculation of the grand total by adding the correlation coefficients of each column. This total is then used to calculate n, which is multiplied with each column sum so as to obtain the first factor loadings of each test. Following this, a cross product matrix is obtained that is subtracted from the correlation matrix to obtain the residual correlation matrix. The residual correlation matrix may have to be reflected so as to maximize the grand total of the matrix. This is done by changing the signs of the factor loadings in the residual matrix from positive to negative or vice versa for the variables both row wise as well as column wise. The second factor loadings are then calculated from the reflected residual factor loadings and they are reflected back to their original signs. Further, factor loadings may be obtained in a similar way. The decision about the number of common factors to extract and retain must steer between the extremes of losing too much information about the original variables on one hand and being left with too many factors on the other. Various criteria have been suggested to understand the number of factors that can be extracted. These are the Fructer formula method, the eigenvalue index method, and the residual correlation matrix method. Post the rotation of factors, the researcher focuses on the interpretation of factors based on its factor loadings. The higher the factor loadings, the more important is the factor on the given variable or test. There are two basic methods of factor rotation: orthogonal rotation and oblique rotation. Orthogonal rotation method is employed when the factors are not correlated with one another, while the oblique rotation method is employed when the obtained factors are related to one another. The scree test is conducted to determine which among the extracted factors is actually repeat. These are the Fructer formula method, the eigenvalue index method, and the residual correlation matrix method. There are two basic methods of factor rotation: orthogonal rotation and oblique rotation. Orthogonal rotation method is employed when the factors are not correlated with one another, while the oblique rotation method is employed when the obtained factors are related to one another. The scree test is conducted to determine which among the extracted factors is actually contributing to the variance and does not measure random error. After the statistical computations of factoring and rotation have been completed, the factors are interpreted by inspecting the pattern of high and low loadings of each factor on the subtests or variables.